So essentially, when you come thinking about technology, as we talk about transistors, of course, a lot of engineering goes into creating uh, basically the modern transistor, like you have in your phones in your pocket. You have about 19 billion transistor. But the physics concept behind this is just understanding what the semiconductor does and perfecting that in the engineering fashion. That's good. Okay, so this is sort of the basis of a lot of what we do. But what else can electrons do? And what we want to talk about today is what electrons do that's beyond just one electron moving around. What I just described to you is just a theory and ideas that just starts with a single electron and just piles electron into different levels, and you get these different behavior. The first example of electrons behaving collectively that was discovered, the phenomena called superconductivity. What is superconductivity? Well, it's superconductor. So what does that mean? You have a conductor like a piece of copper. It conducts electricity. It does it so well. If you cool it down, the electrons basically don't scatter from the vibration of the atoms in the crystal. It conducts a little bit better as you go lower and lower in temperature. A superconductor does something very unusual, which is that at a given temperature, it suddenly has no electrical resistance. And this was discovered actually before quantum mechanics. And it took basically development of quantum mechanics, development of what I just described to you about what's the difference between a metal and insulator to begin to understand what is a superconductor. I'll tell you in a moment why you should care about superconductor. I think a lot of you have probably been inside the superconductor, you just didn't know it. Discuss that in a moment. Now, to understand the superconductor, we need to talk about something called entanglement. Okay? Electrons actually entangle with each other in a superconductor in ways that I'll describe in a moment. At the simplest, you heard about the spooky action at the distance in terms of entanglement. You probably have heard of these words. The simplest way to think about entanglement is just a chemical bond. Bring two atoms together, electron in one atom, and the other electron in the other atom. They want to be not just in the same atom, they want to be also in the other atom. So they create a entangled state in which we can be at both places at the same time. It dictates their properties, how a molecule behaves. Okay? So what does this have to do with a superconductor? So it turns out in a superconductor, I described to you electrons as being independent. It turns out in a superconductor, electrons actually sort of pair up and they find a partner. Once they find this partner, this fantastic zero resistance state emerges. Okay. You say, well, how does that happen? All right. To describe to you how that happens, now I have to give you another important lesson in quantum mechanics, which is that in nature, there are actually, we believe there are only two kinds of particles. You got to get to another kind of particle toward the end of this talk, I hope. The first type is called fermions. Fermions are like very antisocial. Okay, if you think about the energy levels that I described to you, like in an atom, they like to have their space, be in their own energy level. Okay, maybe they can have another partner, but they have to have something different, like they're spinning the opposite to each other to live in that state. Those are fermions. Electrons are fermions, and that's why you fill up those energy levels in a metal. You have to fill them up one by one until you get to the last one. Use up all your electrons. Now, other kinds of particles, bosons. Bosons are a happy bunch. They're very social. What does that mean? It means that if you give them a bunch of energy levels, they don't care how many of them are in one energy level. They can all occupy even the same energy level. Okay? Why is this interesting? The reason it's interesting is that if you have a bunch of boson, as it was proposed by Bose in a letter in a communication with actually Einstein in the 1930s, proposed the idea that if you have a bunch of bosons, have a bucket, bosons can be at different energy levels. If you cool it down at some critical temperature, the bosons decide, you know what? We can all go to the lowest energy, be happy all together. And this state of bosons make a perfect fluid. What is a perfect fluid? Water has viscosity. When you stir up water, it goes around the circle for some time, and at some point, just stops because of its internal friction, this internal viscosity. This is a truly amazing fluid. You stir it, it just keeps going ever. Okay? This is basically our superconductor. When we have electrons and they decide to pair up fermions as individual, it turns out when you pair them together, they become a boson. It's sort of what we call a composite object. And once they do that, they can be happy to create this perfect fluid. Once you have this perfect fluid, it has no electrical resistance. Now, okay, that's a nice curiosity. Is it useful? Or how many people here have had an MRI? Okay, me, I have maybe 100. So if you had an MRI, you were sitting inside a superconducting coil. You know that little tube that they put you inside? It has basically a bunch of wires, looped up like what we call an electromagnet. The technician came some months before you were there. They put a current inside the loop, which makes a magnetic field. They put you in there. They took the power supply away, and that magnetic field stays as long as they keep that basically machine cooled with liquid helium in this case. So the schematic that I have here, just one little loop. Just think about that perfect fluid. When you get it stirred here, if you inject current and make it a current of electrons, these pairs move in a loop, it's just going to keep going forever and ever. And that's what gives you the magnetic field, which we use basically do an experiment on your brain or your ACL, like in my case, to figure out what the hell happened to you on the slopes. Now, there's another thing a superconductor useful for. This little loop of current is the new technology that you may be reading about in the newspaper called quantum bits. Okay, trying to do quantum computing and computing with quantum mechanics. Okay, so what is that all about? So, remember the bits that you may think about inside our everyday sort of technologies is either on or off, 0 or 1. Okay, and now a quantum bit is one in which you can be in the superposition of 0, 1. You don't have to be just 0. You can be 1. You can be actually described as if you have some fraction of 0 and some fraction of 1 described by an arrow on this sphere. How the hell do we make such a thing? Well, here comes superconductor. So if you heard about Google's superconducting effort, basis of superconducting effort on Google is based on something like a superconducting loop in which you have this super flowing current either flowing in one direction or in the other direction. That's the 0 and the 1. And if you can isolate this loop from the environment in a way that it doesn't disturb the property of this loop, this super flow, you can actually put it in a superposition of the two states. So right today, the superconductors that are being the technology that's being used to create, for example, this thing that you might have seen in the newspaper. This is Google's noisy quantum computer. Why is it noisy? Is because when you make this delicate object that has, if you like, current flowing in one way or the other, the superposition of these two is so sensitive to its environment. You have any kind of radiation coming from outside, even cosmic radiation, even if you have your wires not perfectly sort of arranged, you can disturb this quantum superposition. Which is why building a quantum computer today is very hard. Because all the different technologies that we have, and I'll flash them in a moment, rely on this creating this superposition, which in this case I described to you how it happens in the superconductor. So we are kind of in the stage of, I would say, pre-vacuum tubes in terms of computing, classical computing, and the size of the machines are kind of not quite comparable, but the infrastructure required to do this is comparable. So we are trying to get out of this phase to the phase in which we will create technologies that are really, really can do the computing that we want to do. So incidentally, quantum computing is not good for everything. It's not going to give you a better Microsoft Word computing. It's just built for certain class of problems in which this superposition that I described allows you to do computation very, very fast. And, a lot of people are interested in it, including governments, because, you can use this to make a lot of codes, just like that old machine did for the, breaking codes in a different way. So this is kind of comes the point in my talk where I try to describe to you everything that I have said to you about technology, even things that you read today about quantum information, quantum computing. The physicists, these are based on pretty much the things I described to you up to now. In some ways, they are, to us, quite old. Use concepts that are not as modern as things that are discussed here, for example, in Aspen. What do I mean by that? Besides these things, metal, insulator, semiconductor, simple superconductor, which I describe here, there are a lot of different amazing quantum states created by electrons interacting with one another, just like that superfluid I described, which could have amazing application if we could understand them better, not would allow us to understand quantum mechanics better at a level that is undoubtedly is going to have impact. Okay, so how do we go beyond this electrons in a simple metals? Now I describe to you this picture where electrons moving in a crystal, where they jump from one atom to the next, and I describe to you how you get here from an atom. I describe to you how this range of energy of electrons, it turns out that when they have this wide range of energies, electrons actually very weakly interact with one another. What I mean? What I mean is that if I take these bands and I sort of squeeze them, I make a lot of electrons be at the same energy. Well, I do that. Well, one possible way is, I can make the time the electrons spend on every location, on every atom, very, very long. I move the atoms further from one another. It's a long time for electrons to go from one atom to the next. It turns out, throughout the last 35 years, this has given us a lot of different quantum phenomena, which I'll describe in the next 20 minutes, by just making a lot of electrons live in the same energy range. Technical term for this is flat band. You can go next week, come here and ask the physicists, what flat band system are you working on? There are a lot of people working on different kinds of flat band. So what are some of the consequences of this? What are some of the examples? First one is actually the one that gives us technology which I didn't describe, which is a magnet. Okay, so magnet, your refrigerator magnet, the magnet that is used to store information in MRAMs, in the current technology, it relies actually on electrons interacting with one another. What does that mean? That when you force electrons to live in this narrow energy range, it turns out because they are interacting very strongly with one another, they try to all spin in the same direction. And this provides for you this spinning electron provides a sort of a magnetic field. When you have a macroscopic number of atoms, it actually gives you something in which you can, well, it's becoming smaller and smaller. You can store information by having either the magnet pointing up or down. It's like you would have a south and a north pole of any magnet. And this has led to a lot of discoveries in what magnetism is. Just all comes from electrons interacting with one another.